Okay, a little bit about electricity and magnetism, some pretty fundamental stuff. Electric field is force per unit of charge. Charge is measured in coulombs, force is measured in newtons in the SI system. So the SI unit is newtons per coulomb. Electric current is charge per unit of time in a wire or discharge. You pick a point and you measure how much charge is passing per unit of time. Now you can't actually do that. You actually measure it by measuring often the magnetic field that it induces. But anyhow, it's charge per unit of time, and you can't actually measure it by electroplating and so forth. And it's measured then in coulombs per second, amount of charge per unit of time. And that unit is called the ampere. The coulomb per second is an ampere. So coulombs per second, amperes or amps for short, the unit of current. Potential difference is work per unit of charge. And that's in joules per coulomb or volts. That's what a volt is. It's the amount of work you have to do per coulomb to move through an electric field. And that could also be expressed in terms of newtons per coulomb times meters. Now this gives rise to some defining formulas. Electric field is force divided by charge. And of course it follows that force is electric field multiplied by charge. And electric field and force are vector quantities that have the same direction. Okay, charge Q in electric field E is going to experience a force Q times vector E, vector force. Okay, electric current is charge per unit of time, amperes. We use I for current. A lot of times lowercase I, especially if you're not using I for the square root of -1. And sometimes we use J, and often a lowercase j. Easy to confuse with unit vectors. I'm going to stick with capital I. And that's in and I'm writing the unit rather than the relationship. What I want to write this as is delta Q over delta T. And actually, since current can be time varying, with the audience I'm addressing, it's clear I can write that dq dt. Okay, potential. The audience I'm addressing is a student who's been through multivariable calculus. Potential difference is work per unit of charge in joules per coulomb or volts. Okay, so work per unit of charge. So I'm going to say the unit is going to be work over charge, units of work over units of charge, joules per coulomb. And we're going to call that volts. That's what a volt is. That's a definition of a volt. And I think I already said this and then digressed to this, but that's newtons per coulomb times meters. And that's, of course, units of electric field times distance. So we can say that voltage is amount of work per unit of charge, and it's measured between 2 points in space. That might be 2 points in a wire, 2 points in a block of conducting metal, 2 points in an ionized field or whatever, but there it is. And this could also be written as electric field times displacement. Okay, so that we could even write this, dV equals E dot ds. And that's still work per unit of charge between the 2 points. Now, until you do some exercises with this, it won't all make sense. But we want to at least lay the foundations for understanding some of the stuff that you did with Maxwell's equations in the multivariable calculus course. One of the primary areas of application of multivariable calculus is electromagnetics, electromagnetic fields and so forth. Okay, well, so that's good. We've got units for all these things. Now we want to talk about magnetic fields. And I kind of got things backwards when I did this, excuse me, before this, because this relates to one of the videos I did very recently. And this is kind of a follow-up to those videos. Okay, so I'm going to skip down here and say that force on charge Q with a velocity V and a magnetic field B is F mag, and I should have said the force exerted by a magnetic field, and maybe I can. I'll abbreviate it slightly by magnetic field on charge Q with velocity V in magnetic field, which is getting redundant, but we'll just live with it, is F mag. I put the mag on there because I hadn't specified force by the magnetic field, but there it is QV cross B. Okay, that's very simple to understand that. If the magnetic field is up and you have a positive charge moving in this direction, then QV is in this direction. And you do the cross product. QV cross B, the charge is going to experience a force in this direction. If it's moving freely in space, but encounters the magnetic field and otherwise moving freely, it's going to make a loop. That's simply because it's going to experience a force in this direction, but it's going to change its direction this way a little bit, and now it's in this direction. It's going to experience a force perpendicular to this direction because the magnetic field is still perpendicular to it. It's going to come around like this. You work that out. And of course, if it's moving like this and a magnetic field vertically upward, you can still do QV cross B. Okay? It's going to be like this. It's going to turn the thing inward, but it's going to continue moving upward. Okay? It's going to have an inward component, but it's going to be spiraling upward. It's going to not actually exactly be spiraling. It's going to have a helical path. So it's kind of neat to think about that, so it's worth thinking about. Then the one thing I want to kind of get to is the units of the magnetic field. Well, we're saying that the units of QV multiplied by the units of B had better equal units of force. So that the units of B had better be units of force divided by units of QV. And the simplest, most direct way to write this, and of course you can break it down to fundamental units, but I'm going to keep it kind of intuitive, is newtons over coulomb meters per second. Okay? Now, that equals what we call Tesla. That's what a Tesla is. Now, I'll also observe that coulombs over seconds is what? Coulombs per second is the rate at which charge is flowing. That's your unit of current. That's amps. So we could say that equals newtons over amps times meters. Now, when I learned physics thousands of years ago, the fundamental unit, the coulomb was a fundamental unit, okay, just like kilograms, meters, seconds. It's a fundamental unit of charge. We want our fundamental units to be units that can be measured with the greatest possible accuracy. And it turns out that we can measure coulombs with a whole lot of accuracy, but we can measure amps now a a lot more accurately, so the amp is now a fundamental unit, and the coulomb is defined in terms of amps. But the relationships are still all the same. Okay, now we go back to Amperes Law here. Okay, I've got a sketch here. We've got a current I moving along the y-axis. We've got a point P out here somewhere. It turns out in this case it's on the negative x-axis. So we can put coordinates in these things and do all the calculations, but we're pretty adept at doing that, so I'm not going to go through the messy details. And you're adept at doing it. I'm getting less adept at these messy details. Okay, lacking as much working memory as I like to have when I do these things. Okay, so what we have now again is current I, a point P, and an increment of the y-axis. Now we're labeling this increment a delta y sub I because we would typically partition the y-axis into increments with sample points like y sub I star. Okay? And then we're going to let r sub I be the vector from here to here. Okay? Now, I can express the magnetic field contribution delta B at the point P. And I'll call this contribution delta B sub I since I've put a subscript on this interval. Now if we want the total magnetic field at point P, then we partition whatever part of the axis is carrying the current, and we do an integral. Okay? Now, magnetic contribution to delta B sub I at point P is what? Moment of anticipation here. Cross product of the current with the R vector. Okay? So it's a cross product of the current times the length of the increment. Okay? And there's another constant in here. There's a constant K prime. In SI units, it has numerical value 10 to the negative 7th. Very easy to remember. Now you do this in terms of mu's and mu naughts, magnetic permittivities and stuff. You get a little more complicated expression here, but directly related to K prime. And for many reasons, the mu form of this thing is more closely related to fluxes and so forth that we're getting to. But I'm going to use K prime because, again, it's easy to remember. And we'll talk about the alternative expression. Okay, anyhow, delta B sub I is K prime, a constant that has the units. I said it has numerical value 10 to the negative 7th in SI. It has units that make the rest of this equation make sense. You got to get Tesla or newtons per amp meter when you multiply K prime by whatever I'm going to write down here. Okay? So I'm going to multiply K prime by what? I'm going to multiply this by I delta y sub I, product of current and length of the increment. And we're going to cross that with R, okay? But we don't really want to cross it with R. We want to cross it with a unit vector in the direction of R. So I'm going to do it by R divided by the magnitude of R. And this is an inverse square law, very similar to the law of universal gravitation in many ways. Okay, so the further this is from here, well, the effect of this field, or the effect of the current in this increment, magnitude of the effect is inversely proportional to how far it is from the point at which you're calculating the field. There's your inverse R squared. Now, we don't want to cross I delta y sub I, which is one of the sources of the magnetic field. Well, it's actually the source of the magnetic field. We don't want to cross that with R. That would destroy the whole inverse square thing. We cross it with a vector in the direction from here to here. So I could even impose this. Don't have a good place to label it because I wasn't anticipating doing that. And of course we should put a subscript on R since we've got a subscript on R. Okay, there it is. Now what are the units of this thing? Well, vector divided by its own magnitude has no units because the vector will have whatever units, meters, and the magnitude will have units of meters. So we have units of current times length divided by length squared should give us Tesla. Okay? So I'm going to say K prime is 10 to the negative 7th. It's going to be Tesla over what? Well, it's over amps. That's your unit of I, which could be written as coulombs per second if you wanted to, but it's per amp divided by meter. So Tesla per amp per meter Tesla meters per amp. Okay, one side comment I'll make is that an I delta Y is equivalent to a Q. Okay, so I'm sorry, it's equivalent to QV. Has the same units and it has the same function in these relationships. If you've got a lot of charge carriers moving at a velocity, it's moving past per second, it's equivalent to have moving through a distance per second, it's equivalent to having a single charge moving at some velocity. And the velocity would be that distance multiplied by the number of charges you have over here. You can think that through. It's a worthwhile thing to think through. Okay, we'll go on and see where all this relates to some of the stuff I was showing you, although, oh well, no, actually we need to say a little more. Okay, let's observe then that in this case, the I cross the R vector gives us a delta B sub I perpendicular to both. Well, both of these are in the plane, so the delta B sub I has to be in the Z direction. And because of the right-hand rule, it's up. Okay? Another thing, currents in this direction. You put your thumb in this direction, and current surrounds, your magnetic field surrounds the current in a circular manner, which we can see by just considering another point P, let's say on the Z-axis. If you do all this, well then I is going to be, your I delta Y sub I is going to be crossed with a R sub I vector in this direction. It'll be back like so. So if you have a point up here, it's in this direction, the magnetic field will be in this direction. If you have a point out here, magnetic field will be down. And if you have a point down here on the Z-axis, magnetic field will be in the negative X direction. And you have magnetic field surrounding the wire. You can improve on that diagram, and you can do a proof if you wish that shows that at any point the direction of the field is going to be tangent to a circle through the point centered on the axis. Circle in a plane parallel to the YZ plane. Okay? So you can work all that out. Very easy to work out if you have a good command of multivariable calculus.